Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Today we are doing something a little different. We're not just analyzing a document, we're trying to tune in to the core rhythm of the cosmos, the actual beat of space and time itself.
It's a pretty profound idea to start with.
It is. Imagine the entire universe. I mean, everything. All the galaxies, the stars, the empty voids constantly, oscillating. We're talking about the gravitational wave background.
A concept that, for decades, was pure theory. It sounds like something straight out of science fiction.
But it's not. We now know it is absolutely demonstrably real. It is the ultimate cosmic hum.
That's a good way to put it. If you could somehow turn up the volume on the universe, the gravitational wave background, or the GWB, would be this fundamental low-frequency roar you'd hear underneath everything else.
And the one description that really stuck with me from our source material today, a fantastic study from the University of Colorado Boulder, published in the Astrophysical Journal, is that these are ripples in space and time.
Right.
And that these ripples are moving constantly through the cosmos and this is the great part, jiggleous, almost like Jell-O.
It's a fantastic analogy for trying to visualize it.
Isn't it?
It is, though. We should be clear that the jiggle it's infinitesimally subtle. You'd never, ever feel it. But its detection, that is anything but subtle.
A monumental achievement.
Oh, absolutely. It represents a huge triumph for physics, and it's opened up this profound new way of investigating how the largest structures in the universe actually evolve and interact with each other.
And that's really our mission for this deep dive. We want to unpack a massive cosmic mystery that really, it arose the very instant this background was first detected.
The celebration and the confusion arrived at almost the exact same moment.
Exactly. And the CU Boulder research we're looking at offers what might be the most compelling solution to this puzzle yet. A puzzle that has stumped astrophysicists since that groundbreaking GWB detection was announced back in 2023.
Right. And I think to really appreciate the solution, we'd first have to, understand the main players in this enormous cosmic drama.
Let's set the stage.
Okay, so the GWB itself is fundamentally created by this constant, relentless merging of galaxies.
A process that's been going on for billions of years.
Billions of years. It's central to how complex galaxies, like our own Milky Way, actually form and grow and mature over cosmic time.
And at the heart of those mergers, you have the real behemoths.
Yeah.
The anchors of the whole thing.
Exactly. At the core of every significant galaxy, you'll find a supermassive black hole, an SMBH. So when two galaxies are drawn together by gravity, their two central SMBHs are also drawn into this spiraling, inevitable, and ultimately violent dance.
And it's the end of that dance, the collision, that sends out the signal we're talking about.
That's the moment. The final collision of these supermassive black holes sends these incredibly powerful ripples and space-time gravitational waves flooding out into the cosmos.
So if you just zoom out across all of cosmic time, you've got billions of years of these galaxies merging, billions of these black hole collisions.
Right.
And all of them are contributing their own individual ripples to this subtle, omnipresent background hum.
That's it exactly. That cumulative, overlapping signature is the gravitational wave background. It's like, imagine turning on 1 trillion distant radios all at once and just listening to the collective static they generate.
And this brings us right to the heart of the puzzle. The one data point that made this whole field of research just turn on its head.
The big reveal.
Yeah. In 2023, several big international collaborations, the most prominent being NanoGrav, that's the North American Nanohertz Observatory for Gravitational Waves, they announced they had done it. For the first time, they had definitively detected the GWB.
An earth-shattering moment for gravitational wave astronomy. I mean, a Nobel Prize-worthy discovery, without a doubt.
But then they looked closer at the signal itself.
And that's where the confusion started.
Yeah.
They'd found the song, but it was being played far, far too loud.
Exactly. When they measured the waves, they were significantly, shockingly, larger than anyone had predicted.
All of the best theoretical models, the most sophisticated simulations we had, they all pointed to a much quieter background.
So you have this clear, massive discrepancy between what the physics models calculated should be there and what our observations were actually showing us.
Right. And as Julie Comerford, the lead author of the study we're focusing on, said when she saw the data, it was a surprise and a fun new puzzle to figure out.
A fun puzzle, I guess, if you're a brilliant astrophysicist. For everyone else, it was just a massive mystery.
And that's exactly what her team set out to solve.
Okay, so let's try to unpack this cosmic symphony. We need to really establish the fundamental concept of the GWB because, the name is familiar, but the physics behind it is just vast.
It really is.
Let's start with that analogy you liked from the source material, the swimming pool, just to make it a bit more concrete.
The swimming pool analogy is probably the best way to visualize what's happening. So picture a massive cosmic-sized swimming pool. This pool represents the entirety of space-time.
Okay, got it.
Now, imagine there are lots and lots of people in this pool. These people are the galaxies, and more specifically, they're merging black holes. And they are all constantly moving around, kicking, splashing.
And every one of those splashes, every kick, that's an individual gravitational wave being sent out by a black hole merger somewhere in the universe.
That's it, exactly.
Yeah.
And the gravitational wave background is just the accumulation of all of it, the overlap, the interference pattern of every single one of those individual waves happening all across the universe over billions and billions of years.
So you don't feel one distinct splash, you just feel the constant chaotic churn of the water.
You end up with a constant wash of overlapping ripples across the entire surface of the pool. That's the background.
No, I think a really critical piece of context here is the scale, because when we talk about gravitational waves, a lot of people probably think of the first ones that were detected by LIGO.
Right. That's a very important distinction to make.
Those came from much smaller stellar mass black holes colliding, and those waves were, well, they had very high frequencies, relatively speaking. They were like a quick, sharp chup.
That's a crucial difference. The LIGO waves are in what we call the acoustical range, hundreds of hertz. They last for a fraction of a second. You can literally convert them into a sound, that famous chirp.
But the GWB we're talking about now, the one detected by nanograph, that's in the nanohertz range.
Nanohertz. I mean, it's an almost incomprehensibly low frequency.
What does that actually mean, nanohertz?
It means one single cycle of one of these waves takes billions of seconds to complete.
Billions of seconds. So years. Many, many years for one wave to pass by.
Decades, even. And the reason the frequency is so incredibly low is because the source is just so vast. The nanohertz signal corresponds to the waves generated by those supermassive black hole binaries we were talking about.
These aren't two sun-sized objects. These are behemoth.
Gargantuan systems. You have two black holes, each millions or billions of times the mass of our sun, orbiting each other. Their orbits are huge, sometimes taking several years or even decades to complete. So the waves they emit are themselves incredibly long, low-frequency ripples that stretch across light years of space.
And it's the slow, steady, enormous oscillation that makes up the GWB.
That's the symphony. It's not a quick chirp, it's the deep bass note of the universe.
And yet, I mean, even though the sources are so massive, the actual effect on us is still basically nil, right? We're being jiggled like jello, but we don't feel a thing.
Correct. The waves have stretched out and weakened over cosmic distances. They're so incredibly subtle that we require instruments of just unimaginable sensitivity to even detect them. And this really brings us back to the source of those ripples, the mechanics of how galaxies evolve.
So walk us through that mechanic. How do two huge galaxies, miles apart, end up with their central black holes in that final, fatal dance?
Well, the universe is constantly building bigger things from smaller things. It's a hierarchical process. Gravity is always at work, pulling smaller galaxies into the orbits of larger ones.
So you have countless galaxies constantly colliding and intertwining all over the cosmos.
Yes. And as two large galaxies start to merge, their two supermassive black holes, which were at their respective centers, begin to lose orbital energy.
How do they lose energy?
Primarily through a process called dynamical friction. As they move through the now combined galaxy, their immense gravity pulls on all the stars and gas clouds around them, creating a sort of gravitational wake.
Ah, so that wake pulls back on them, slowing them down.
Exactly. It's like cosmic drag. This friction robs them of their orbital energy, causing them to spiral inward, closer and closer to the new center of the merged galaxy.
And that's when they enter that final spiraling dance.
Precisely. They form a binary system, orbiting each other, getting faster and closer, till they eventually, well, they coalesce into a single, even larger black hole.
And that final moment, the coalescence, that's the big splash.
That's the moment that releases a tremendous burst of energy in the form of these nanohertz gravitational waves, sending those ripples out through the cosmos.
So in terms of the broader context, why does charting this background, why does it matter so much to astrophysicists? What's the big prize here?
The big prize is that the GWB is effectively a fossil record of galaxy formation.
A fossil record?
Yes. By studying the specific details, the frequency, the amplitude, the whole signature of these waves, we can learn so much. It reveals new insights into the evolution of the universe itself.
How so?
Well, if we can correctly model the GWB, if we can understand why it has the strength it does, we can basically reconstruct how galaxies have been merging over the last, say, 10 billion years. We can understand how smaller, simpler, what we call primordial galaxies coalesced over time to create the large, complex structures like the Milky Way that we see all around us today.
It's a direct probe into the history of cosmic construction.
It's one of the most direct probes we could ever hope for.
Okay, let's talk about the size differences, because this is really where the assumptions that everyone was making fundamentally went wrong. When we say supermassive black holes, it sounds like one category, but it's not.
It's not at all. It's a huge category that spans an enormous range of masses.
So on the upper end, what are we talking about?
On the upper end, you have the true giants. These are SMBHs, with a mass equal to billions of times the mass of our sun. These are the absolute powerhouses capable of generating incredibly strong individual waves when they collide.
The heavyweights of the universe.
Absolutely. But then you have the secondary category.
Which are still huge by any normal standard.
Oh, of course. You have the ones that are still supermassive, but as the study says, slightly less so. Their masses are only millions of times larger than our sun.
Only millions.
Right. So in the context of a galaxy merger where you have, say, a billion-sun SMBH meeting a million-sun SMBH, that million-sun object is considered the secondary or the smaller player in that particular dance.
And this is where we get to the crucial piece of conventional wisdom that this new study completely challenged. Why were those smaller black holes, the million sun mass ones, why were they basically ignored in the models for the GWB?
It really came down to the basic physics of how gravitational waves are generated. The amplitude or the strength of the wave scales very significantly with the mass of the objects that are colliding.
The bigger the splashers, the bigger the wave.
Exactly. And because the waves produced by a merger between 2 billion sun SMBHs are so overwhelmingly powerful, the prevailing theoretical models basically assumed that the cumulative contribution from all those smaller million-sun black holes would just be negligible.
It would be lost in the noise from the bigger events.
Correct. Or that their contribution would be too low frequency to be relevant to the bulk of what nanograv was actually measuring.
So, to be clear, the models that existed before 2023, they focused almost entirely on the biggest, most massive sort of equal mass mergers, the big-on-big collisions.
That's right. They were trying to calculate the expected strength of the GWB by focusing on those heavyweight fights. They just assumed that the contribution from all the big-on-small mergers was just too quiet to really matter.
They minimized the role of the medium-sized players in this cosmic symphony.
They did. They assumed a much more, predictable pathway for how these things contributed. And it was that minimized expectation that the nanograv anomaly just completely shattered. So let's really focus in on that specific data point, the one that made all this new research necessary. When nanograv finally successfully detected the GWB, they didn't just say we found it. They provided a measurement of its amplitude.
Its overall strength or loudness.
Exactly. And that amplitude measurement immediately defied all the expectation.
And again, we're not talking about it being just slightly off. This wasn't a minor calibration issue.
No. This was a significant statistical outlier. The measured waves were substantially stronger than predicted.
How much stronger are we talking?
The estimates vary a bit, but perhaps as much as 50% larger than what the most sophisticated current theoretical models had predicted.
50%. Wow.
Yeah. It's a huge number, and it forced astrophysicists into a really difficult position. If the real universe is generating waves that are this much stronger than we predict, then our model is fundamentally flawed. Something is missing.
So if the actual waves are bigger than the model predicted, you're missing a source of amplification. And logically, it seems like you have two main paths to investigate that.
Go on.
Well, either there are just way more mergers happening across the cosmos than we thought there were.
A higher merger rate.
Or the black holes that are involved in the mergers we do count are somehow effectively larger than we assume them to be when they collide.
That's a perfect summary of the two main possibilities. And this is where a critical point about the data comes in. If the discrepancy was simply because there were more mergers overall, that higher merger rate, that would typically show up in a different way in the GWB signal. It might change the slope of the background spectrum across different frequencies.
It would change the character of the sound, not just the volume.
A good way to put it.
Uh-huh.
But the specific shape and the magnitude of what nanograv detected, it strongly favored the second idea, that the individual events themselves were just more energetic.
So the data was pointing toward the mass involved in the collisions being larger, not just the sheer number of collisions being higher.
Exactly. The conclusion was that the current models of how these SMBH mergers work must be missing a key factor, a factor that amplifies the wave strength right at that moment of coalescence.
And if the solution wasn't something, within the known physics of how galaxies evolve, what was the alternative?
Well, the alternative was what people started referring to as requiring new exotic physics.
Which is always exciting, but also a little scary for physicists.
It is. It means maybe there are entirely new populations of black holes we don't know about, or some cosmological phenomena we hadn't even conceived of. And this is why that 50% discrepancy was so shocking. It opened the door to some pretty wild ideas.
So let's go back to our swimming pool analogy. If the waves in the cosmic pool are way bigger than you expect,
Right.
it means either we have a lot more swimmers in the pool than we counted, or the swimmers we did count are suddenly doing much bigger cannonballs than we estimated they could.
And the data was just screaming that the cannonballs must be bigger.
So why does a bigger cannonball make a bigger wave? Let's get into the physics of that.
It goes right back to Einstein's theory of general relativity. When these two immense masses spiral together and crash, the amount of energy that gets converted and released as gravitational radiation scales non-linearly.
Non-linearly, meaning a small increase in mass gives you a big increase in wave strength.
A disproportionately large increase in the gravitational wave amplitude. It depends on the total mass of the system, but also critically on the mass ratio between the two black holes.
Okay, so the logical conclusion here seems pretty inescapable. If the measured waves were substantially larger than predicted,
then the supermassive black holes involved in those mergers must have had a larger effective mass right before they collided than our models assumed they had.
they were heavier at the finish line than they were at the starting line.
In a manner of speaking, yes. And this is precisely where the brilliant hypothesis developed by Comerford and Simon comes into play. They decided to go back and revisit that original assumption.
The one that said the smaller million-sun black holes didn't really matter.
Exactly. They started to ask a very simple question. What if those black holes aren't that size right at the moment the waves are created? What if?
Wait.
What if they grow significantly during the merger process itself?
That's the intellectual pivot right there. That's what unlocks the whole mystery.
It is. It means you have to stop looking just at the starting mass that we measure from galaxy surveys, and you have to start looking at the dynamics during that several million-year period when the two black holes are spiraling in toward each other.
What happens in the dance itself?
Correct. The researchers hypothesized, and this was based on some hints from earlier simulations, that when a smaller SMBH starts to merge with a much larger one, something strange happens. The smaller black hole seems to undergo this incredible, unexpected growth spurt.
It gains a lot of mass very quickly.
A lot of mass, pushing it up into a mass range where its eventual collision generates a wave that's powerful enough to dramatically influence the GWB measurement. It transforms that black hole from a negligible ripple maker into a significant cannonball maker.
So the player we had dismissed from the team as just a minor league contributor suddenly became a major force on the field.
And that unexpected extra energy from all these newly promoted players provided the missing 50% amplification. It was exactly what was needed to match the nanograph data.
And this mechanism, this differential growth, that's the key.
It's the key to resolving the whole anomaly. It explains where all that extra wave amplitude comes from without needing to invent any new or unknown forces. It just means our calculation of the black hole's mass at the moment of collision was wrong because we weren't correctly accounting for how much they eat along the way.
So this is where the discussion really gets into the nitty-gritty physics of how this growth spurt actually happens. And what's so great about this explanation is that it's not some mysterious new phenomenon. It's a simple, almost elegant quirk of geometry and the environment during the merger.
Yes, what the scientists termed preferential accretion.
Preferential accretion. Let's break that down.
To understand it, we first have to really visualize the environment. We need to remember that a galaxy merger is anything but a clean, neat event. When two huge galaxies collide, the entire system is just violently disturbed.
The source material called it a messy affair.
And that's putting it mildly. It is a colossal disturbance on a galactic scale. And crucially, all the massive amounts of gas, which is the primary raw fuel for making stars and for growing black holes, that gas from both of the original galaxies gets violently shocked and starts to funnel inward toward the center of this new combined system where the two black holes are spiraling around each other.
So all the food in the new house gets pushed toward the two biggest mouths.
Exactly. And this inflowing gas doesn't just fall in randomly. It creates a specific structure that defines the entire feeding process.
And what does that structure look like?
It creates a large, dense, donut-shaped cloud of gas that surrounds the binary black hole system at the center. This cloud is absolutely vital because the gas it contains will eventually fall back into the black holes.
A process called accretion.
Right. And this accretion is what causes the black holes to grow larger. It's also what releases immense amounts of energy, sometimes making the galaxy's center shine as a brilliant quasar.
Let's spend just a moment on the physics of that accretion process, because it's not just stuff falling gently into a hole.
No, it is a highly dynamic and incredibly efficient process. As the gas spirals inward, it doesn't fall straight in because it has angular momentum. It forms a disk.
An accretion disk.
Yes, and in that disk, friction and gravitational shear cause the gas to heat up to millions of degrees. It becomes an intensely hot, glowing plasma. And it's the sheer efficiency of converting mass into energy through this frictional process that allows black holes to grow so rapidly and release such immense power. The material spirals in, sheds its angular momentum, and finally crosses the event horizon.
Okay, so we have the picture. Two black holes, one massive one and a secondary smaller one, and they're spiraling toward each other inside this massive, hot, gaseous donut. The question is, why does the smaller one get the lion's share of the food?
This is the core aha moment. And it was revealed by some previous computational simulations that Comerford and her team studied very closely.
Yeah.
And it comes down entirely to where the two black holes are located spatially within that gas cloud.
It's a cosmic real estate issue. Location, location, location.
It's precisely that.
Yeah.
Location determines destiny in this case. Let's look at the critical positions of the two black holes. The more massive black hole, because it's the gravitationally dominant partner, it tends to carve out a path for itself closer to what we call the barycenter. That's the gravitational center of the whole binary system's orbit.
So it's right in the middle. And intuitively, you'd think that's a prime spot. That's where you want to be to capture the most gas?
You would absolutely think so. But here is the completely unexpected twist. Because of the complex dynamics of the accretion disk, things like centrifugal forces and the way the two black holes orbit and clear out gas, the very center of that donut, the region closest to the larger black hole,
Yes.
is actually where the gas is sparsest. It's a low-density region. It's almost like a hole in the middle of the donut.
You're kidding. So there's a surprising famine zone right where the biggest mouth is sitting.
That's it, exactly. Meanwhile, the smaller black hole, the secondary SMBH, is forced by the binary's orbital mechanics to orbit a little bit further out from that central barycenter.
Okay.
Its orbit is situated much, much closer to the dense inner rings of that gas donut structure.
So the smaller black hole is perfectly positioned to intercept the maximum amount of all that fresh inflowing fuel before it even gets to that sparse region in the very center.
That is the defining takeaway. The gas is being funneled inward from all directions. But because the smaller black hole is located further out, it's closer to where the bulk of the available fuel is constantly being replenished. The secondary black hole just intercepts and preferentially accretes more of that fuel than its gigantic partner.
And that is preferential accretion.
That's the mechanism.
That distinction is just incredible. It's not that the smaller black hole is gravitationally stronger or that it's inherently hungrier. It's that the flow dynamics of the gas, dictated by the orbit and the geometry of the merger, simply give the feeding advantage to the secondary black hole.
It completely overturns the intuitive assumption that the most massive object always dominates the feeding process. The massive one may have more raw gravitational power, but the environment of the merger gives the secondary black hole the superior geometric position during that crucial spiraling phase.
Now, let's talk about the significance of this. So the smaller one goes faster, but it's still way smaller than the original behemoth, right? Why is this 10% or 20% growth so incredibly consequential for the gravitational wave background?
Because the entire process, this in-spiral phase, lasts for millions of years.
Right, it's not a quick event.
Not at all. So even a small preferential gain in its mass accretion rate, if you sustain that over the entire time scale that the black holes are spiraling and accelerating towards their collision, it can drastically change the final mass of that secondary black hole.
We're not talking about a small change then. Over millions of years, you could be adding, what, tens of millions of solar masses to that smaller black hole right before impact.
Exactly. And since, as we said, the gravitational wave amplitude scales so dramatically with the mass of the colliding objects, or cannonball analogy, that final state of the secondary black hole is now heavy enough to produce a much, much stronger wave than what its original pre-merger mass would have ever predicted.
And that provides the necessary amplification to match the stronger nanograv data.
It's the missing piece. It shows how a subtle dynamic detail happening across these vast cosmic timescales can cascade up into a massive cosmological effect that we can actually measure today.
But wait, let me just challenge this a little bit. If the smaller one is growing so fast, why doesn't it eventually catch up to the massive one? Why don't you end up with a near equal mass merger, which would produce an even stronger wave?
That is a fantastic question. And the answer is that while it is growing preferentially, it rarely, if ever, manages to fully equalize the masses. The initial mass difference is just too enormous to overcome. 1 million versus 1 billion is a huge gap.
So it closes the gap, but doesn't erase it.
Right. But, and this is critical, the efficiency of gravitational wave generation is maximized when the two merging black holes are closer to being equal in mass. So by preferentially growing that smaller partner, you are making the mass ratio closer to 1:1. And that dramatically increases the power of the final wave output compared to what you would get from a highly unequal mass merger.
Yeah. So it's not just about making the smaller one bigger, it's about making the pair a more efficient wave generator.
That's the key. That refinement in the mass ratio is the true source of the enhanced GWB amplitude.
I have to say, this research has such an intellectually satisfying conclusion to it. They didn't just find a problem, they identified a physical mechanism, this preferential accretion, and then they rigorously tested whether putting that one single effect into the existing models could actually solve this real-world, observed cosmological mystery.
The methodology they used, the CU Boulder team, was just wonderfully targeted. The lead researcher, Julie Comerford, she started with this detailed set of equations that already captured all the known physics of galaxy mergers.
So the standard models, the ones that were failing to match the nanograv data.
Exactly. And then she and her team made one single adjustment to these complex theoretical frameworks.
Just one tweak.
One tweak based on the physics that they inferred from watching the gas dynamics in those simulations. They adjusted the growth rates within their equations to specifically model that differential growth dynamic.
And that's where the 10% figure comes in. They modeled this preferential accretion by making the smaller black holes grow, specifically 10% more than the larger ones.
That's right.
Why that number? Why 10%? Was that just a random guess, or did the physics actually dictate that specific number?
It wasn't arbitrary at all. That 10% figure was arrived at iteratively. They ran detailed numerical models of the accretion process over these long timescales. They were looking for the minimum necessary increase in mass amplification for that secondary black hole that would be required to push the GWB amplitude high enough.
To close that 50% gap.
To close the gap. And their simulations suggested that, given the geometry and the orbital mechanics we talked about, a preferential gain of around 10% was a physically plausible, even conservative estimate for what was required.
So it wasn't just a mathematical plug-in number, it was an estimate that was actually rooted in the observed mechanics of the gas density and the flow.
Exactly. And the outcome of making this one specific adjustment was, well, it was definitive.
What happened when they ran the models again?
It was immediate and conclusive. That single 10% tweak modeling, that slightly accelerated growth of the secondary SMPH during the in-spiral, it was precisely enough to reconcile that long-standing discrepancy. The revised estimates of the gravitational wave background, now with this preferential growth baked in, they lined up perfectly with the actual surprising measurements from the nanograv experiment.
So the mystery it solved itself. Not by adding some new exotic object to the universe, but just by understanding that we were grossly underestimating the smaller black holes right up until the moment of impact.
We were underestimating how much fatter they were getting and how much faster than we ever saw.
Incredible.
It really is. And it reinforces the central takeaway from their study, which is that the little ones, they do start out small, but as they put it, because the little ones grow the most, they shouldn't be discounted. Their accelerated growth during that merger phase transforms them into really effective contributors to the overall background noise, strong enough to explain the entire amplitude anomaly.
This feels like a major victory for the refinement of these astrophysical models, especially for this new field of nanohertz gravitational waves. But the team is, rightly careful. They note that this is a possible solution, not the complete final answer.
As any good scientist would.
So the mathematical model works beautifully, but science demands empirical validation. What are the next steps? How do you go about confirming this hypothesis?
That next phase is absolutely crucial, and it's also incredibly difficult. While the math provides this really strong circumstantial evidence, the scientific process now demands observation. So the team has already launched a new effort that's focused on observing real galaxies that are currently in the act of merging.
They need to catch this preferential accretion happening in the wild, so to speak, before the final collision happens.
Precisely. And this is a huge challenge because these mergers take millions of years to unfold, and the objects are just vastly distant. You need extremely sensitive telescopes to be able to resolve the gas dynamics in these binary black hole systems.
What are they looking for specifically?
Specifically, they need to measure the gas density distribution right around the spiraling pair. And if it's even possible, they need to try and measure the actual accretion rates onto both the primary and the secondary black holes.
And what would be the smoking gun? What specific evidence would constitute confirmation?
The smoking gun would be if their telescopic observations consistently show, across multiple merging systems, that the gas distribution is indeed geometrically skewed, that the smaller black hole is consistently sitting in a denser region of that inflowing material.
And then show that it's actually eating more.
Exactly. If they can also show that the smaller black hole has evidence of a higher accretion rate relative to the gas that's available to the larger black hole, that would provide the necessary empirical confirmation. You would prove that preferential accretion isn't just a good idea in the simulation, but a dominant mechanism in these mergers across the cosmos.
So if we just zoom out one last time, how does resolving this nanohertz gravitational wave mystery, how does it connect to the biggest, broadest cosmic picture? What's the real relevance of this work for you listening at home, trying to understand how the universe evolved?
This research, it really tackles one of the most fundamental and enduring scientific questions there is, which is the formation and the evolution of supermassive black holes themselves.
How they got so big so fast.
Exactly. Despite decades of incredible advancements, we still have these massive gaps in our knowledge about how these cosmic behemoths formed so quickly in the early universe. As Comerford herself notes in the study, I've spent my career studying supermassive black holes, and we don't even know how they form.
Which is truly an astonishing statement when you think about it, that nearly every major galaxy is built around one of these things, and we don't know where they came from.
It is. And this study provides a crucial piece of that puzzle, specifically regarding the growth mechanism. It helps us tackle the question of how the black hole seeds in the very first primordial galaxies, which were tiny and made up mostly of gas, how they could have possibly built themselves up to the gigantic black holes that we see existing today.
And the early universe was immensely gas-rich. So if this preferential accretion mechanism is a dominant growth mode, it would have been incredibly efficient back then.
Oh, absolutely. Think about it. If a merger in the early universe, where gas was just everywhere, consistently meant that the secondary, smaller black hole underwent a dramatic 10% or more growth spurt, that provides a very rapid and very efficient pathway to build up huge black hole masses in a relatively short cosmological timescale.
So mergers aren't just about building bigger galaxies. They're the primary engine for building bigger black holes.
It suggests they are, particularly for the already existing smaller seeds. It gives us a much clearer picture of the violent, messy, yet highly effective process by which the universe assembled its largest and most powerful engines.
This has been a truly fascinating dive into one of the universe's greatest new riddles. So, to quickly recap the journey for everyone, scientists detected the gravitational wave background back in 2023, confirming this rhythmic oscillation of space-time itself. But there was a problem.
A big one. The waves were surprisingly strong. They were too big, too loud for the sophisticated models, which had really emphasized the mergers between the biggest of the big black holes.
And the really elegant solution, the one proposed by the CU Boulder team, it wasn't some giant new phenomenon or exotic physics. It was something much more subtle. It was the overlooked growth of the smaller black hole in a merging pair.
This preferential accretion. It happens simply because the smaller black hole has a geometrically superior seat at the cosmic dinner table. It gets to intercept all that inflowing gas fuel before its gigantic partner does.
And by just incorporating this 10% preferential growth rate into the models, suddenly everything clicked. The theoretical predictions aligned perfectly with the nanograv observations.
And it provided this potent explanation for where all that extra wave energy was coming from.
It's just a powerful reminder that sometimes the biggest cosmic mysteries are solved by looking much closer at the dynamics of the players that seem at first to be the smallest.
Absolutely. And that really leaves us with a final thought for you to mull over.
Yeah.
We've shown that the dynamics of gas accretion, these messy environmental factors that happen inside a galaxy merger, are just so vital. They dictate the final mass of these supermassive black holes, and because of that, they dictate the strength of the gravitational wave background that we measure today.
Right.
So if a subtle geometric advantage like that can completely overturn our understanding of mass growth, what other seemingly minor environmental factors might be out there? Things we haven't even considered yet, maybe related to early stellar feedback or magnetic fields. What other minor details might have secretly determined the characteristics of every galaxy, including the specific merger history that shaped our own Milky Way?
We've resolved one major discrepancy, but it opens the door to so many more questions.
It does. The implications of this discovery are a big reminder of just how much is still fundamentally unknown about the formation processes of the largest, most foundational objects in the entire cosmos.